All right, so 2 weeks ago we started looking at the reactance of a capacitor, and then last week we started looking at the reactance of an inductor. And the main purpose of doing this, of running these experiments, was to gain a better understanding of the relationship between voltage, I shouldn't do this, I should just, we'll have another current source here, to look at the relationship between the voltage across a reactive component and the current going through it, right? Knowing that the reactance, right, of a capacitor, or the impedance of a capacitor is what? It's mathematically, it's complex value, right? So when we look at the reactance of a capacitor, it's given by what?
1 over J omega C.
Very good, Peter.
Perfect.
I'm impressed.
1 over J omega C, right? So, so then we looked at what happens, right, when the current goes through it. We looked at the voltage across it using Ohm's law to get IC times ZC, right? And that was basically just this, right? And then we looked at, now if this current is a sinusoid, when it gets multiplied by this imaginary value, we introduce a 90-degree phase shift, right? In the case of a capacitor, the 90 degrees was which way? So the voltage was leading or lagging?
It was
lagging.
Oh, wait,
Right.
it says leading and lagging.
So,
Are you on the inductor?
no, so the inductor, for an inductor, right?
Inductor.
Because this, right, this becomes, if I bring J to the top, it becomes negative I J 1 over omega C. And so then this, in the complex plane, falls over here on the J axis. This is the J or imaginary axis, and this is the real axis. So it falls over here, and so I get negative 90. Right? So it's a lagging. Voltage will be lagging the current.
Or leading to 270.
Or leading to 70. Right?
Wait, but it's
But when you start,
yeah, it's actually.
right, it's actually lagging. Right? Hey Shiva.
Hello.
So that's the main, right? The main thing that we want to master. What these complex things are doing. And then last week we started looking at an inductor, and we did it in SPICE, and we saw that in the case of an inductor, again, if I put a current source, right? The current that comes through it, and then I look at the voltage, right? That again, we have VL equal to IL ZL. Now, what is ZL?
J omega L.
J omega.
Because it's
Peter, the only one that remembers this stuff?
So it's just too early.
Well, yeah, I was
So-
thinking it's inverse.
Right.
Yeah,
So VL would be IL J omega L, right? And so this one, since it's positive, it falls over here, and so we get a plus 90 degrees shift. So therefore, voltage in the case of an inductor is it leading or lagging? Leading. It's leading the current, right? So, phase difference between voltage and current of a particular component, which is reactive, capacitor and inductor. Okay. Any question on that? And so I think you guys ran the simulation, and what was left was to actually build the circuit. If you remember, for the capacitor, then we wanted to actually build a circuit and make the measurements over a range of frequencies, right? And what we did was we said, okay, well, instead of how can we create a current source, right? One way was to put in, okay, I'll draw it here. One way was to put in a very large resistor here. So this is a voltage source now. A voltage source. And I can put in a very large resistor. When we say very large resistor, what do we mean? It's always, everything is relative, right? So when we say that resistor is large relative to what? The impedance of the inductor, right? As long as this resistor is much larger than the impedance of the inductor, in really the amplitude, the magnitude of it, over the range of frequencies that we're looking at, then what happens is when we look at, do you guys remember this? We'll go over it again. So we said, if I want to find the current going through this whole circuit, how would I find it? I have a voltage source, right? And I have an impedance. Ohm's law. Okay, so I would be equal to what?
V over
V over Z, right? Where Z in this case is what?
ZL plus R.
So ZL plus R, exactly, and ZL was?
J omega.
Is Peter the only one that knows this stuff?
No, they're talking about it too, they're just quiet. Okay, so when, and then again, so we're looking at the magnitude, right? So then that would be square root of omega squared L squared plus R squared, right? Complex number, imaginary or real squared plus imaginary squared is that, right? Okay, so we are interested in resistance values that are much larger than the magnitude of the ZL, right? So we're talking about R's that are much bigger than omega M over the range that we're going to look at. Okay, well, at low frequencies, we're good, right? Because why? At low frequencies, when omega is small, and let's say let's say the inductor is around 100 microhenry, right? This is 10 to the negative 6, right? This is 10 to the negative 6, and R is even around 100 ohms. What does omega need to be before this value is comparable to the resistance?
Very large.
Yeah. It needs to be, well, 10 to the 6.
Yeah.
If it's 10 to the 6 and then multiply by 100 micro, then I will get about 100. So as long as I'm staying, so let's even reduce it by a decade. So as long as my omega is smaller than 10 to the 5, then this resistance is going to be much bigger than omega L, right? So then this Z becomes approximately equal to R, right? So then from there, current just becomes V over R. So effectively, I have created from here to here a current source, where the current is defined by just V over R. Right? Over the range of frequencies that I'm going to vary, that current is not going to change by much. It's going to stay pretty much constant. So then I can just measure the voltage here, and knowing the resistance, well, we can already figure out what the current is, then we can write those values down, right? And then compare them, just like the way we did it for the capacitor. And then, so that's one way of doing it. But the way I ask you guys to do is you actually measure this voltage, the difference between here and here, right? Remember, you have two probes, and then using that, you find out the actual current value, right? Now, why do we do that? Why do we say, okay, go ahead and measure these things over several frequencies? What was the whole purpose of it? We were actually trying to determine the value of a reactive component. In the case of the capacitor, we wanted to find out what that C is. If I give you an unknown capacitor or an unknown inductor, and I ask you what is the value, that's one way of doing it. Right? Do you guys remember how we did it when we were looking at the rise time and fall time? This is just way too early in the morning.
Oh, wait, wasn't it with the? Didn't you do that in the workshop?
We talked about it in the workshop too.
The 95%
Exactly.
is 3RC.
Oh,
Right.
That.
So, in the case of the capacitor, we looked at this charge time, and we actually looked at the 95%, when the voltage reached 95%, and then we looked at this time, right? And this was supposed to be equal to 3RC, and then from there we could figure out what C is. Okay? In the case of an inductor, it's actually the voltage drops like this, and so we look at when it reaches 95%, when it drops by 95%, so this would be at 5% of the max, and then again we would take this, and this was equal to 3 R over L. It's actually L over R. L over R. Okay, and again, we measured it, and then we could figure out what L is based on that, right? So that was by looking at the charge times, right? Here, we're going to be measuring these voltages over different frequencies. Even at a single frequency, what you can do, because we know that VL is equal to IZL, right? And ZL was J omega L, right? And then if I look at the magnitude of VL, that's just I omega L, right? You guys see that? So if I have voltage, and I have the current, right? And I have the frequency at a particular frequency, L would be VL over I omega, or 2 pi F. So I can find my inductance by doing this. Right? The only trick was we were looking at the VL max because we were looking at the sinusoid, and then this I max, and then realizing, because we know that these are 90 degrees out of phase, you're going to take those two values at the max points, even though on the scope they might not line up, and you take those values, then you make this calculation, and you find what L is, right? And then we want to do it over several frequencies to get an average. Any questions? Is that clear? Peter knows. Peter knows what we do.
I know some of it. But...
Okay, why don't you come up, Peter, and explain the part of it that you know.
inductor, right?
Yes. We're trying to find the inductance of an inductor.
And we do that by what?
Right.
So we're just gonna build this circuit,
Uh-huh.
and then we're gonna through the oscilloscope, we're gonna create a voltage. And
Armand,
then-
are you paying attention? Okay.
and then put in a 100 ohm resistor, and then we measure the VL max and the I max, and then we find out, right?
Okay. And where do we measure? So how are we going to measure the I max?
On the oscilloscope,
How?
get the math function or the cursors, and then put it on the top.
Exactly. Right. So where are your two probes? Where are you putting your two probes?
So for VL max, probably right here,
Mm-hmm.
and then for I max, probably.
So that part I didn't specifically go over, right? But who knows? If I want to find I,
It's
how can I find I?
after the resistor.
So we do have a probe there already, right? So
Right. 'Cause you said I equals V over
so
R.
Peter already put a probe here,
Right.
right, to measure VL, the voltage across the inductor, right? All right, now, so I can measure this, right? So in this equation, I know this. I'm setting the frequency, so I know that. I need I.
I guess you can put it anywhere on the circuit, right? Because current is the same.
Okay,
Series.
but we gotta, somehow I gotta figure out what that is. So walk me through the whole thing, right? So first of all,
Oh wait, what?
actually if you look at it,
But what for fine? Yeah.
right, so how are we gonna do that, huh?
Because we just do I equals V over R. We don't even look
Okay,
at,
so I is equal to V
right.
over R.
we don't even look at ZL in this case.
Okay, so this V is what?
Uh,
Right, it's V in minus
Oh,
V L over R. So that's why I need another probe here, right? Now I can do the math function that says V in minus V out to measure that, right? And then in my spreadsheet, I know what R is, I do the division and I get the current. Okay? And again, the important thing that I want to bring your attention to is this, that this, once I do this, right, and I get the current, it's the current through the resistor, which is also the current through the inductor, right? Because it's a series circuit. So if I were to draw that, if this is my current, this voltage across the inductor now, how would that look like?
What?
So if this is the waveform for the current, right? So it's V in minus VL over R. Let's say it looks like this. And that is the current.
well, what's VL?
And it's also the current going through the inductor, right? If it looks like this, what would the waveform for VL look like?
That 90-degree shift.
Which way?
That one. Leading.
Leading, right? If it's leading, then it means that this max will happen first
Right.
by 90 degrees, right? Because this is 1/4 of the period, so it's 90 degrees. So that for the inductor, it will look like that. Not as good, but you get the point, right? So when you look on the scope, when you do the math function, you should see exactly this. They're going to be 90 degrees out of phase. And so then, to find out, you measure VL at the max you measure I at the max, you plug it into this equation, and that gives you the inductance. Okay, so do I need to go over this again, or you guys are good? Maybe we should just do it. Let's just do it, and then if there are questions, we'll answer it. So I know Shiva has been putting these in the spreadsheet. We'll do this again today, but I really would like for everyone to become comfortable with working with spreadsheets.
Someone can use my laptop.
So yeah, or you know,
Oh,
you
yeah.
can bring one of those machines. You can do it in Google Sheets or whatever. It's a really powerful tool in studying things, and I've mentioned it before. Even though there are so many different tools, engineering tools, I still go and I plug things in. My first go-to program is Excel. I'll just go and put in the equations and then look at the curves, and visually helps me understand what's going on. Okay, so let's get the equipment, let's build it, test it, and see how it's going to look like. So again, this was to give you guys a solid understanding of what reactive components do with respect to the phase, right, between the voltage and current. And later on we'll go back. Remember at the beginning we started with an LC circuit when we had the inductor and the capacitor. And Mr. Winters was saying, you know, at a certain frequency that impedance becomes 0. It's because that, remember, for this one the voltage is leading, for this one the voltage is lagging. At a certain frequencies the voltage and the voltage on this one and this one are 180 degrees out of phase, right? Because this is 90, that one's 90. 100 degree out of phase. If you look at our complex plane again. Yeah, if I look at our complex plane, if the voltage for one of them is here, 180 degrees out of phase puts it here, they cancel each other out. That's what was happening. Okay?
Oh.
And we'll look at it more carefully later.
I thought you were gonna draw that.
Or, yeah, well, it's the same effect, right? It's going to
Yeah.
be, yeah. So the next thing we're going to do, and Peter has asked this before, and to all of you guys, it's like, where do we use these circuits, right? So we have a good understanding of the phase now. We're going to look at what happens if we do something like this. We'll analyze it today quantitatively, right? We're going to talk about it intuitively, what's going to happen, and then next week we're going to go through the math and spice and all of that. So if I have a voltage source again and put a capacitor here, and then go to a resistor to ground, and I want to look at the voltage here now. And let's call this is my output voltage. This is my input, this is my output. And this, let's say this is a signal, it could be like an audio signal, right? But we're going to show it as a sine wave for now. Okay? So, knowing what you know about capacitors, can somebody walk me through if this frequency changed from low frequency all the way to high frequency, what would happen to the voltage here? Just walk me through it. So knowing what you know about capacitors. What is the question I usually ask about capacitors? I go, you have a frequency going through the capacitors. What is the question I usually ask?
High frequency?
Right.
Is it open or a
Right.
Short.
So let's start with low frequencies, right? So at low frequencies, the capacitor is what?
Open.
Okay?
Wow.
And you know that now. Before we looked at it physically, because low frequencies, what happens, the capacitor gets charged and then you don't get it. It's just gonna stop, it's not gonna let the current go through, right? Mathematically, impedance of a capacitor is what?
1 over J
Zero
omega
omega.
C.
So if this omega is 0
Infinite.
or low, this impedance becomes really, really large. So the really, really large impedance here is kind of like an open circuit,
But
right?
it'll go down.
Yeah. So for low frequencies, this is an open circuit, so you're not going to get much current going through. Or it's a really large impedance, so you're not going to get much current going through. If I have a very small current going through this resistor, this voltage is going to be what? Small or large? Small. Right? Small current times the resistance is going to give me small voltage. Now, as the frequency goes up, what happens?
It comes up.
Short.
It becomes a short. So it's kind of like just putting this over here. So the voltage will approach your Vn. Right? So if I were to draw what happens with the output over frequencies, at low frequencies it's very small or close to 0, and then it goes up until it reaches Vn. If this is my P out and this is Vn, right? And this is over frequencies, right? And this is what we said, what? If you're doing something like that, what's a fancy name for this? Sorry? It's a filter,
Oh, yeah.
right? I'm filtering out low frequencies,
Right.
right? So this is like, you know how in your stereo you have knobs for increasing and decreasing the bass, and then you one for treble?
Yeah.
This would be for a treble, right? Because
Wow.
it lets your higher frequencies go through.
Oh.
It's going to take out your lower frequencies.
You should
Wow.
design a speaker.
I bet we
That's what
can.
we design a
can.
speaker.
We can, if we ever get back to our audio amplifier, we can do something like this. right?
Wow.
Now, so this was to get the treble out, right?
Right.
What if I want to get the bass out? Can you guys-
Inductor.
Oh my god, that's why high five.
So if I go like this
Oh my God.
to another resistor, this one, so this is called this VL out, and this is VC out. This would look the other way around. It would be like that. So that's going to let the bass go through, and it's going to cut out the higher frequencies.
Yes.
So you're seeing the applications of your favorite components, right?